Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study prime elements in a ring. I have written definition for prime element, then we shall see some examples and we shall prove some results. The definition is a non-unit and non-zero element denoted by P of a ring R is called a prime element of R if we can write P is equal to AB, where A, B are in R, then one of A or B is a unit in R. Then P is said to be prime element. The condition is it is a non-unit. Unit element we have seen every invertible element is said to be unit element. So it should not be unit element, and it is expressed as it is not unit and not zero element. And it is expressed, if it is expressed as P is equal to AB, then one of A or B is a unit in R. For example, in the ring of integers, which we denote by Z, in the ring of integers, Z with addition and multiplication operation, what will be the unit elements, or what are the unit elements? In number theory, if you consider the set of integers, then the primes are defined as P is greater than 1 and the divisors of P, and only divisors of P are 1 and P itself. P divides 1 divides P and P divides P. Then this implies P is prime in the number theory. This is our usual definition earlier, but here what is difference here is P is expressed as A into B, where A, either A or B is a unit in R. Now what are the units in Z? The units in Z are -1 and -1, because these are the only elements which are invertible. They have their own inverse. Inverse of 1 is 1, inverse of -1 is -1, and therefore these are the elements which are unit in Z, and therefore the primes in this ring set of integers will be those primes with negative sign or negative of the numbers. That means then the prime elements are in Z are, see, in number theory we have seen the prime elements are 2, 3, 5, 7, then 11, 13, 17, etc. These are the elements which are prime, and here we shall consider this with the negative of positive and negative also, and thus the prime elements in Z are to be considered as plus or -2, plus -3, etc. because it can be multiplied by 1 or -1, and plus -11, etc. These are the prime elements in Z. Second example can be considered as the ring of real numbers. In the ring of real numbers, R with usual addition and multiplication. Now what are the prime elements? See, every element is unit. We have seen earlier in every non-zero element, every non-zero real number has multiplicative inverse, and therefore every non-zero element is a unit because it is invertible. Since it is invertible, and therefore every element is a non-zero element is a unit, and the condition for prime element is it is non-unit and non-zero, and therefore there is no prime in the ring of real numbers. there is no prime element in this ring of real numbers. So thus in integers these are the prime elements, but in the ring of real numbers there is no prime element. Now we shall prove a lemma for Euclidean ring. Taking Euclidean ring, then every non-zero element in R, is either a unit in R or can be written as product of a finite number of prime elements in R. There is also this similar theorem in number theory, which is a fundamental theorem of arithmetic. That means every integer greater than 1 can be expressed, either it is a prime or can be expressed as a product of prime in a unique manner. So that is similar to that. Every non-zero element in Euclidean ring R is either a unit or it can be expressed as product of finite number of prime elements. Prime elements just we have defined here in R. Now we shall prove it. Let A not equal to 0 and A belongs to R be an element in R, and we shall prove the theorem by taking induction on D value of A. Prove the result which is written as a lemma. We shall prove the lemma by taking induction, mathematical induction we shall use by taking induction on D value of A, that is D of A. It is a Euclidean function. In Euclidean ring is defined by taking D value of a non-zero element, which is this is non-negative integer. D value is non-negative integer. Now how we shall use the induction on D value of A? In the method of mathematical induction there are two steps. First we shall prove this result is true for certain D value, and then we shall prove that the result is true, assume that the result is true for every element which has the D value less than a certain value, and then prove it for the next higher value. So that is our first step of induction we shall consider as first step of induction. We have A is equal to 1 into A, and for A belongs to R, it is non-zero, and therefore what is D value of A? D value of A is D value of 1 into A, and this is certainly greater than or equal to D value of 1. This is the property of first property of Euclidean ring. D of AB is greater than or equal to D of A, and thus D value of 1 is minimal in the ring of in Euclidean ring R. Therefore 1 is the unit element in R which has minimal D value. And now we know that, so if D of A is equal to D of 1, then A is a unit. A is a unit in R. This result we have proved in our earlier lecture, units in a ring. You may refer that. If D value of A is equal to D value of 1, then A is a unit in R, and therefore we will have here the D value of 1 is minimal, here we have written, and thus this proves that the theorem is true for d value of 1, because A is a unit. So it is expressed as a unit. Either A is unit or A can be expressed as product of finite number of prime elements. Here A is a unit, and therefore this proves the theorem is true for d of 1. Therefore, the result or the lemma, we have written it as a lemma. Lemma is true for d value of 1, that is d of 1. And now we shall consider the second step. So this we shall take as first step of induction. The result we have shown is true for d of 1, and now we shall assume second step of induction. We shall have to assume the result is true for all values, d values of x. We shall take d values of all elements which are less than d value of a, and then we shall prove the result is true for d value of a. That is second step of induction. Suppose or assume the lemma is true. Is true for all elements x, for all x belongs to R, such that d value of x is less than d value of a. So we shall assume those elements, the result is true whose d value is less than d value of a, and now we shall prove the result is true for a. We shall prove that the result is true for a. Then this is the second step of induction. Then the result is true and the theorem will be proved. Now if A is a prime, see A is a unit, or we see we have it is either a unit or can be written as a product of finite number of prime elements. If A is a unit, then there is nothing to prove, that we get the result. A is a unit. There is nothing to prove. And that means we shall assume that A is not a unit. Then A can be written as product of two elements B into C. Suppose A can be written as A is not a unit and A is written as A is equal to B into C. B, C belongs to R, where neither B nor C is a unit. That means here A is not a prime. A is not a prime and A is written as B into C. Now we will have this relation as D of A. Or we will consider like this D of B. D of B is less than D of BC. Why? Because B and C, none of them is a unit, and therefore the relation is strictly less than. D of B, usually D of B is less than or equal to D of BC, but here B and C, neither of them is a unit, and we have proved this result also. then d of b is strictly less than d of bc. But what is d of bc? D of a, because bc is a, and d of c is strictly less than, just as above, d of bc. D of c is strictly less than d of bc, and which is again d of a, and thus d of b and d of c both less than d of a. And by our assumption, whenever d of x is less than d of a, the lemma is true for x, and therefore this shows that the lemma is true for b and c. Therefore d of b is less than d of a and d of c is less than d of a. And by this assumption, when d of x is less than a, the lemma is true for x. Therefore the lemma is true, or the result is true for b and c. And what is the result? This one. B and c are not in it, and therefore it can be expressed as, b can be expressed as a product of finite number of prime elements. Therefore b and c can be expressed as, or can be written as a product of finite number of prime elements. So let b is written as product of finite number of prime elements, and let us suppose b is written as product of p1, p2, pn, and c is written as primes q1, q2 and qm, where p's and q's are primes, that is p1, p2 etc., and q1, q2, qm etc. are primes in R. These are primes in R. And now we can write A is B into C. A is B into C. And what is B? B is P1, P2 up to Pn, and C is Q1, Q2 up to Qm. And what this shows, A is expressed as finite number of primes, n plus m, and thus this shows that the result is true for A. Thus A is expressed as a product of finite number of prime elements, and therefore the lemma is true for A. And this is what we wanted to prove as our second step of induction. Assuming the lemma is true for all elements whose d value is less than A, we have proved it is true for the d value of A. And this completes the proof. If you consider the ring of integers, then this theorem can be easily verified. So if you have, say, this element as 48, then it is not a prime. So it can be factored into primes. So this can be written as say 4 into 12, and again 2 into 2, and this can be written as 2 into 2 into 3. These are the primes, p1, p2, etc. Or if you can consider as 105, then this is 15 into 7, or which is 5 into 3 into 7. So thus this is the usual theorem in number theory, but we have proved the same theorem in ring theory, taking Euclidean ring. Next we shall define what are relatively prime elements. As next definition, let R be a Euclidean ring and let ABC belongs to R. A divides AB belongs to R, then the two elements A comma B belongs to R are said to be relatively prime if their greatest common divisor is a unit in R. So this is the definition for relatively prime elements. And as usual, we have in number theory the elements, say 5 and 7 are relatively prime because their greatest common divisor of 5 and 7 is 1, or that of 4 and 7, 4 and 11 is also 1, and therefore these are relatively prime, and it is a unit. It can be considered as a unit because here we consider the negative of the elements also. And now another way of saying it is that if A and B are relatively prime, then their GCD is 1, then GCD of A and B is equal to 1. This is notation for GCD. So this is the definition for relatively prime. Now next result we shall consider or prove as a lemma, and it is let R be a Euclidean ring and let ABC belongs to R and A divides BC, but GCD of A and B is 1. This is notation for GCD. A and B is 1, then A must divide C, then A divides C. So this is the result. That means A divides the product B into C, but the GCD of A and B is 1, means A does not divide B, then A must divide C. That is the meaning. So see, we know 2 divides say for example 4 into 7. Then the GCD of 2 and 7 is 1, therefore 2 divides 4. So this is the meaning of the result. We shall prove the result. We know that the GCD of A and B can be expressed as can be expressed as the combination of A and B, can be expressed as lambda A plus mu B, where lambda mu belongs to R. A, B already are in capital R, and thus GCD of A and B is written in this form. That is, GCD of AB is equal to lambda A plus mu B, but this is 1, Therefore, this 1 is equal to, it is given, it is 1. 1 is equal to lambda A plus mu B. Now what we shall do is multiply both sides by C. Multiplying it by C, we have C is equal to, this is C, 1 into C is C, lambda AC plus mu BC. This is the relation that we will have. And now we suppose this as 1. Now we have A divides lambda AC, or first we can write A divides AC. These are simple divisibility relations we have studied earlier in our earlier lecture. A divides AC because A is a factor here, and given A divides BC, C, A divides B into C, and this implies A divides mu into BC. Or we can write this as A divides lambda AC, A divides mu into BC. Here if A divides AC, then A obviously divides lambda AC. So in place of AC only, we shall write lambda AC. And now what this gives, A divides lambda AC, A divides mu BC. And again this together implies A divides addition of these two. These results we have proved earlier, that lambda AC plus mu BC. And thus, but what is lambda AC plus mu BC? It is C, and therefore that gives this, thus A divides C, and this proves the result. If GCD of A and B is 1, then A divides C. Now one more lemma we shall prove is, if P is a prime element of Euclidean ring R, and P divides the product A into B, AB belongs to R, then P divides A or P divides B. P divides one of them, P divides A or P divides B. So this is the result. Or this can also be considered as a definition, second definition for prime element. P is prime element and P divides A into B, then P divides A or P divides B. The proof is simple for this. Suppose P does not divide A. P does not divide A, and then this implies the GCD of P and A is 1. And if GCD of P and A is 1 and P divides AB, then by this lemma, see, A divides BC and GCD of A and B is 1, then the alternative is A divides C. And thus if P divides AB and GCD of P and A is 1, then we must have P divides B by earlier lemma, and thus one of them divides, P divides one of them. If P does not divide A, then P divides B, and conversely if P does not divide B, then GCD of P and B is 1, then P must divide A. So thus in this lecture we have seen a definition of prime element in a ring, and then we have proved a theorem which is factorization theorem. Every element which is non-unit, every element which is non-zero in Euclidean ring is expressed as it is either a unit or expressed as finite number of product of prime elements, and these two lemmas we have proved. I hope you can understand this. Thank you for watching the lecture.